Okay, so the purpose of this lecture and the following lectures is to show that every complex torus is essentially what is called an elliptic curve, an elliptic algebraic curve. Okay, so I will start with an element in the upper half plane, namely the set of all complex numbers with imaginary part positive. Okay, and then you all know that there is a lattice associated with tau, which is the set of all integer linear combinations of 1 and tau, the set of all n plus n tau, where m and n are integers. And then you know that there is a torus complex one dimensional torus associated with tau, which is just the complex plane modulo this lattice. And here what we mean by this is we take the set of equivalence classes of complex numbers where the equivalence is given by two complex numbers are said to be equivalent if they differ by an element of the lattice. Okay, we can also think of this lattice, elements of this lattice as translations by the corresponding elements. So this can be viewed also as a subgroup of Mobius transformations of the complex plane, and this is just the set of orbits under the action of this subgroup. Okay, so this is also the orbit space, set of orbits. Okay, and then we have seen that there is a Weierstrass P-function associated to this complex torus. So it is so it's phi tau of z is the Weierstrass phi-function associated to tau, and you know that this satisfies a differential equation. So it satisfies the following differential equation, namely the derivative of the phe-function squared is equal to 4 times the cube of the function minus I guess it was g2 times phi minus g3 minus g3 tau. This is the differential equation, and in fact if you factorize the right side into linear factors, you get 3 linear factors which we write as phi tau of z minus e1 into, so phi tau of z minus e1 of tau into phi tau of z minus e2 of tau into phi tau of z minus e3 of tau, where obviously e1 tau, e2 tau and e3 tau are zeros of the derivative of the Weierstrass P-function, and they are the only 3 distinct zeros in any fundamental parallelogram. Okay, and e1 of tau has been, you know, this was defined by is the value of the phe-function at half, e2 of tau is the value of the phe-function at tau by 2, and e3 of tau is the value of the phi function at 1 plus tau by 2. Okay. So, so this is the this is the first order second degree differential equation that the Weierstrass phi function satisfies, and in fact so I had explained in one of the earlier lectures, I had indicated that it is the algebraic nature of this equation, which is if you think of phi tau and phi prime tau as variables, then you are getting a cubic equation, and that indicates that hints that there is something algebraic going on behind this. So what we will do is we will put x to be, we will call the variable x to be phi tau of z, okay, and then we will put y is equal to phi prime tau of z, okay. We will set these two variables, and what we will do is and if you rewrite this equation, you get a polynomial equation, an algebraic equation. You get y squared is equal to 4 x cube minus g2 tau x minus g3 tau, okay. We get this equation, and so what we can do is this is a polynomial in two variables x and y, and therefore what we can do is you can look at ordered pairs in C2 which is C cross C, Cartesian product of C with itself, which satisfy this equation. So you are looking at the zeros of this polynomial in C2, okay. So so let me write that. So well let so I'll use this notation xi tau 2, I'll explain this notation later. Let xi tau 2 be the subset of C2 defined by the zeros of this polynomial. Y squared is equal to 4x cube minus g2 tau into x minus g3 tau. You look at all the, so that means that that is xi2 tau is a set of all lambda mu in C2 such that lambda comma mu satisfies this equation when you put x equal to lambda, y is equal to mu. So so I was getting mu squared should be 4 lambda cube minus g2 tau lambda minus g3 tau. So in this connection, please do not confuse this lambda with the partial elliptic the partial elliptic modular function that we had defined in some time ago. These lambda mu are just constants, okay. So so this is the set of zeros of this polynomial in C2, okay, and now what we can do is that from the, so you know this so we have the complex plane, and the complex plane and then you have the complex plane minus the lattice. This is the open set that where you have taken away all the lattice points, okay, and then you have, of course you have this quotient of this by the lattice to give you the torus, the complex torus, and of course if you take this as an open subset here, this is an open subset. If you take the quotient, what you will get is an open subset here, that will be the torus minus the let me call this as x naught, where x naught is the image of the whole of the whole lattice. Okay, you know that this map is invariant under the under translations by elements of L tau, because after all this is the quotient map. Okay, so all the points of the lattice, they will go to the same point below on the torus, and let me call that point as x naught. Okay, so let me call this map as pi sub tau of the set L tau is actually x naught. Okay, so now the point is that we know that the Weierstrass P-function is basically a function which is meromorphic on the complex plane, which it has a double pole at each point of the lattice, and with residue 0, and therefore from C minus, from this open set you actually have the phe-function as this is actually a holomorphic function. If I put phi tau, this is a holomorphic function, okay, and similarly you also have the same for the derivative of tau, phi prime tau, that is also holomorphic, because you see phi prime tau had poles exactly at the again at the lattice points, and they were poles of order 3. Okay, they were poles of order 3, and therefore and these were the only singularities. Therefore phi prime tau is also a holomorphic map from this to the complex plane. So what we will do is that we put these two together and try to define a map into C2. Okay, so what we do is so let me write this once more. So you have from complex plane minus L tau to now I am going to define a map into C cross C, which is C2, and the map is you send Z to the ordered pair phi tau of Z, comma phi prime tau of Z. You send it to this ordered pair, and so you have this map, and it's holomorphic in each variable. Okay, because in the first variable it's just the map Z going to phi tau of Z. In the second variable it is the map Z going to phi prime tau of Z, and so long as Z varies outside the lattice, this is a holomorphic function. So this is a holomorphic map. Okay, and you know the point is that so if you call this map as so let me call this map as phi sub 2, let me call this map as phi sub 2, then it is very clear that the image of this map goes into this subset. Okay, because if I call the first variable as lambda and the second variable as, if I call this as lambda and that as mu, then because of the differential equation lambda and mu will satisfy this condition. So it is very clear that this map lands inside this. Okay, so phi 2 of so the image of phi 2, so image of phi 2 lands inside psi tau inside this subset. Okay, then and yeah, and I want to say that I just want to say that this map I want to say that the image is exactly that, and I want to say that this this is a bijective, it's in fact it's a bicontinuous, it's a homeomorphism. I want to say that it is a homeomorphism. Okay, so to prove that, see the first thing, see first of all it's a non-constant holomorphic map, and a non-constant holomorphic map is an open map. Okay, so first and foremost this is an open map, alright, and secondly I'll show that I'll show that this map is both injective as well as surjective. Okay, so the claim is phi2 is bijective. The claim is that this is a bijective map. Okay, the claim is it's a bijective map. So what do I do for that? So we will prove injectivity and surjectivity. So so the first thing is in order to prove injectivity and surjectivity, we will have to recall certain properties of doubly periodic functions, okay, which we have already used long before in one of our lectures, but I will have to recall those things. So so the first thing is, let me tell you that why phi2 is surjective. Why is phi2 surjective? So you see, so you take an ordered pair lambda comma mu in psi sub tau upper 2. Okay, so please think of this 2 above only as a superscript. Please don't think of this as square of something. Okay, the reasons for this putting the superscript will be clear after I introduce projective space, okay, which I will do so very soon. So you take a point here, okay, and I will have to show that there is a z here such that phi tau of z is lambda and the phi tau prime of z is mu. I will have to show that. Okay, so the fact that this ordered pair is in this set means that lambda mu satisfy this equation. So let me write that down first. Mu squared is 4 times lambda cube minus g2 tau lambda minus g3 tau. Now so let me recall the following fact, that if you take the interior of the fundamental parallelogram and translate it suitably so that the boundary does not have any of the lattice points, then the number of zeros of an elliptic function is equal to the number of poles in that region. Okay, and what that says is that the elliptic function takes the value 0 as many times as it takes the value infinity, and replacing the elliptic function by the elliptic function plus an additive constant will tell you that it will take minus of that constant, the value minus of that constant also as many times as it takes the value infinity. Okay, so we know that phi has a pole of order 2 at each of the lattice points, and if you translate the fundamental parallelogram so as to avoid all lattice points on the boundary, you will get exactly one lattice point inside, and therefore the number of times the phe-function will take the value infinity in the interior will be exactly 2. Okay, and it will be at that point, which is at that lattice point which is a pole of order 2. Okay, and therefore it will take any other value also 2 times in the interior. Okay, so we can always find a z0 such that phi tau at z0 is equal to lambda. Okay, so we can always find find z0 such that, so z0 not in the lattice such that phi tau of z0 is equal to lambda. Okay, but on the other hand, but we know that that by virtue of the differential equation satisfied by phi, we know that phi prime tau at z0 the whole squared will be 4 times phi tau of z0 minus 4 times p tau of z0 the whole cube minus g2 tau into phi tau of z0 minus g3 tau. So that will be 4 times, but phi tau of z0 is lambda, so it will be 4 lambda cube minus g2 tau lambda minus g3 tau, and this is by assumption equal to mu squared. So which will imply that phi prime of tau of z0 has to be plus or minus mu. Okay, and recalling the fact that phi prime is an odd function, okay, we can replace if phi prime of, so we are also trying to find z0 so that phi prime tau of z0 is actually equal to mu. Okay, so if phi prime tau of z0 is minus mu, replace z0 by minus z0 so that phi prime tau of z0 will become plus mu, and the value of phi of tau of z0 will not change because phi is an even function. Okay, so replacing z0 by minus z0 and noting and recalling that phi tau of z is even while phi prime tau of z is odd, we can get phi tau of z0 is equal to lambda and phi prime tau of z0 is equal to mu. Okay, so this gives you the surjectivity, right. The next thing that one has to do is injectivity. Is injective. So I'll have to say something here. So I think there is a problem. So there is a problem with my statement here again. So in fact I have not written this right correctly. In fact what I wanted to say is that since the map phi2 is also invariant under the action of L tau, it goes down to a map from the complex torus minus the point which is the image of the lattice, and I want to say that is the one that is bijective. Okay, so this statement is not accurate, so I'll replace this now. Okay, phi2 is surjective, and for the injectivity when it goes down, the statement is that if phi2 takes the same value at 2 points, then the 2 points differ by a lattice, point of the lattice. Okay, so let me make that change. Let me make that change here. So okay, so phi2 is surjective, and phi2 is surjective, and phi2 of z1 is equal to phi2 of z2 if and only if z1 minus z2 is in the lattice. Okay, so basically so let me again correct myself. I am not claiming that phi2 as I have defined it is injective, is bijective. The point is that it goes down to a map from the torus minus a point, the point being the image of the lattice, and it is that map which I want to say is bijective onto this subset. Okay, so surjectivity is there, and apart from that you do not have injectivity, but 2 points going to the same point should tell you that the difference lies in the lattice. Okay, so that is what I will have to prove. So well, yeah, so so here, so let me prove the second part. So yeah, so what we will do is you can we can argue various cases. You know that in the fundamental parallelogram there is exactly, if you take the points in the interior, there is exactly one point corresponding to the the equivalence class of a given point under the lattice. In the interior there is only one representative, whereas in the boundaries, if it is not, the 4 vertices are 4 representatives for the point that goes to x0, for the points that go to x0. Okay, then apart from these 4 vertices, along opposite edges you will have 2 points as representatives for points whose orbits intersect the boundary. Okay, so I'll have to look at various cases. So what I'll do is I'll first assume that let me first assume that Z1 and Z2 are actually inside the fundamental parallelogram. They are in the interior of the fundamental parallelogram. Okay, and then I have to literally say that they are equal, because if the difference is in the lattice, if they are inside the fundamental parallelogram and the difference is in the lattice, okay, then the only possibility is that they are one and the same. Okay, so next assume, so let me draw a line here. Next assume that phi sub is there, yeah, phi sub 2 of Z1 is equal to phi sub 2 of Z2 with Z1 and Z2 in the interior of the fundamental parallelogram. So the fundamental parallelogram is the one that is formed with vertices 0, 1, 1 plus tau and tau. Okay, so assume that these two are in the interior of the fundamental parallelogram. Okay, therefore then we will have to show that Z1 is equal to Z2. Okay, in other words, phi2 when you restrict it to the interior of the fundamental parallelogram is actually injective. Okay, so now for this we will have to do a little bit of integration. So what one does is so one does the following thing. So you see, so let me draw a picture. So I have, this is the tau plane, rather this is the z plane. Yeah, in all these things tau is fixed. Okay, this is the z plane, and I'm just looking at the mapping omega is equal to phi tau of z. Okay, and what I'm going to do is, so here is 1, this is 0, this is the real axis, this is the imaginary axis, and so here is my tau somewhere here, upper half plane, and I have this parallelogram 1 plus tau. Okay, and you see so these so I'll put these points with a cross. These are precisely, these 4 points are precisely the poles of phi as well as phi prime. The phi function has a pole of order 2 with residue 0 at each of these points, and phi prime has a pole of order 3, okay. And then we also know what the zeros are, the zeros of phi prime are. So the zeros of phi prime are precisely here. There is a 0 at half, okay, there is a 0 at half, because you know, if you look at that so you see yeah, when I put z is equal to half, alright, then E1 tau is p tau of half, and then this vanishes, so phi prime vanishes. So the zeros of phi prime are at 1 by 2, then there is 1 0 at tau by 2, and then there is a 0 here, 1 plus, which is 1 plus tau by 2, okay. These are the 3 zeros, and let me put a circle around these things to tell you that these are zeros. And of course if you so you will also have zeros here and here, okay, because phi prime is after all periodic, doubly periodic with periods 1 and tau. So this point will also be a period, I mean this point will also be a 0 of phi prime, and that is going to be 1 plus, this is going to be 1 plus tau by 2, okay, and this point will also be a 0 of phi prime, that will be 1 by 2 plus tau, okay. So these are all these crosses which are circled, these are the zeros of phi prime, okay. These are all the zeros that I have in this fundamental parallelogram, including the boundary, and there is only 1 0 in the interior, okay. And as far as the poles are concerned, the poles are exactly these 4 vertex points, alright. So this is my diagram. Now I have taken Z1 and Z2 in the interior of the fundamental region, okay, and so let me first assume, let me first look at the case when neither of Z1 or Z2 is this 0, okay. So suppose Z1 is not equal to this 1 plus tau by 2, and it is not equal to Z2 also, okay. Suppose these are distinct from this point, okay, then see what you do is so here there is omega plane, this is the omega plane, so I have to omega plane. So what you do is, your situation is that you have a point, you have Z1, so I'll use a thickened dot for Z1 and I'll use a thickened dot for Z2, okay. And what you can do is you know, I can just I can draw a path from Z1 to Z2 that avoids any of the, you know, any of these marked points, namely the poles of phi and phi prime and the zeros of phi prime, okay. And what I can do is I can also find a simply connected neighborhood of that path which does not contain any of these zeros of phi prime or poles of phi or phi prime, okay. So I can find this path and I can also find, so let me draw that. So I can find this let me call this as something, let me call this as u, okay. So this path is gamma, let me call this path as gamma. So gamma is a path in the interior of the fundamental parallelogram from Z1 to Z2, avoiding zeros of phi prime of Z and poles of phi of Z and phi prime of Z, okay. And u, of course you can find u a simply connected neighborhood of gamma, also avoiding the poles of phi and phi prime and the zeros of phi prime, okay. U is a simply connected neighborhood of gamma in the interior of the fundamental parallelogram that does not contain poles of phi of Z, phi tau of Z, phi prime tau of Z and 0 of phi prime tau of Z, okay. Now so if you now look at see the if you look at the function given by the right hand side of this equation, namely this, the function on the right side of this equation, okay, namely you take 4 phi tau Z cube minus g2 tau phi tau of Z minus g3 tau, that function is an analytic function in this on u, okay, and the point is that it does not vanish, because you have avoided, because where it vanishes are exactly the zeros of phi prime tau, okay. So you have an analytic function on a simply connected neighborhood, on a simply connected set which does not vanish, then it has a square root, okay. So this analytic function will have a square root, and you can find an analytic branch of the square root that is equal actually to phi prime tau of Z in on u, okay. So let me write that down. The function 4 times phi tau of Z cube minus g2 tau phi tau of Z minus g3 tau is analytic, that is holomorphic and non-vanishing on u, which is simply connected. So it has a analytic square root, a branch of the analytic square root which is equal to phi prime of tau there, okay. So has an analytic branch of, so let me write that here. So it has an analytic branch of square root of this function, that is a analytic square root, okay, which equals phi prime tau. Okay, I can find an analytic branch which equals phi prime tau, right. Now what you do is that you now consider the integral integral over gamma of phi prime tau sub z dz by square root of 4 this quantity look at this integral, okay. Then this integral is actually, because there is an where here I have taken in the denominator, I take the analytic square root which is equal to phi prime tau of z. So this integral is just going to be so this is going to be, the denominator is also phi prime tau of z, so it is just integral dz, okay, and gamma is varying from z1 to z2, so I will just get z1 minus z2. This integral will be z1 minus z2 by, because we have taken the analytic branch like this, okay, z2 minus z1, because the terminal point is z2, yeah, you will get z2 minus z1. But on the other hand, what you will have is that on the other hand actually this integral is 0, this integral is actually 0, because you see you write omega, you make a change of variables, you make a change of variables by omega is equal to phi tau of z, you change the variable of integration from z to omega. Then so if I call this integral as I, then what you will get is I will also be integral from phi tau of z1 to phi tau of z2 of d omega by root of 4 omega cube minus g2 tau omega minus g3 tau. This is a valid change of variables, and but then you have assumed that phi tau, you have assumed that phi 2 of z1 is phi 2 of z2, so that means that you know phi tau at z1 and z2 are the same, phi prime tau at z1 and z2 are the same. So what this will tell you is that these two are the same, alright, therefore this integral is 0, okay. So the point is that in principle you are integrating over the image of gamma in the omega plane, and that would be a closed path starting at phi tau of z1 which is equal to phi tau of z2, okay. But the point is that you are able to there is an analytic branch of this square root, okay. So therefore this integral is actually 0, okay. So if you put these two together you get z1 equal to z2, okay. So this will tell you, so this is equal to 0, so z1 equal to z2, okay. So this proves that when z1 z2 are in the interior and different from the 0 of phi prime, okay, then these two being equal will tell you that z1 and z2 are one and the same, okay. So we will have to look also at a few other cases. So suppose I assume z1 is 1 plus tau by 2, that is the case that I will have to look at. So if z1 is 1 plus tau by 2, since this is a 0 of phi prime of tau, okay, you will get phi prime sub tau of z1 is 0, okay, and but you see phi 2 of Z1 is equal to phi2 of Z2 is our assumption, okay, and this tells you that that phi tau of Z1 is the same as phi tau of Z2, and phi prime tau of Z1 is equal to phi prime tau of Z2, okay, and let me assume that Z2 and Z1 are in the closure of the fundamental parallelogram, okay. So let Z1 Z2 belong to the closure of the fundamental parallelogram, okay, and you take Z1 to be this 0 at the center of phi prime, okay. Then since phi prime is 0 at Z1, phi prime is also 0 at Z2, and therefore for Z2 the only choices are these other points, okay. For Z2 these are the only choices, but at those points, but whichever of those points it is, the phi value at that point should be the same as the phi value at 1 plus tau by 2, okay. But remember that the phi value here is E1, it is E1 of tau, phi value here is E2 of tau, and phi value here is E3 of tau, and we have already seen that these three are distinct numbers, okay, they are distinct complex numbers, therefore we will get a contradiction, okay. So if for example Z2 was this, okay, then you will get the phi value at Z2, the fact that phi value at Z2 is equal to phi value at Z1 will tell you that the phi values are the same here and here, okay, but the phi value here is the same as the phi value here, so that will say the phi value here is the same as phi value here, but the phi value here is actually E1 and the phi value here is E3, and you are saying that will say that that E1 is equal to E3, which is not possible, okay. So because of the distinctness of the EIs, okay, it will follow that Z2 will also have to be 1 plus tau by 2 in this case, okay. So let me write that, then phi prime tau of Z2 is 0, the fact that E1 of tau not E2 of tau and E3 of tau are distinct shows that Z2 also has to be 1 plus tau by 2, and that has to be equal to Z1, okay. So we have settled the case when one of them is the 0 at the center, and then we will also have to look at the case when Z1 is one of these zeros on the boundary, okay. So let's take that case. Next, let Z1 be one among half plus tau by 2 and tau by 2 plus 1, okay. Then again phi prime vanishes at Z1, so that will tell you that phi prime has to vanish at Z2, okay, and well then then I would like to say that Z1 and Z2 are exactly on the opposite side, on the opposite edges, either if they are on these or two opposite edges, then they differ by tau, and if they are on these two opposite edges they differ by 1, okay. So you will have to look at the situation where they are not you should say that it cannot happen that this is Z1 and that is Z2, okay, that is the case you will have to say. and well, essentially in that situation the phi values being the same again will tell you that E1 is equal to E2, okay, for example, and that is not possible, okay. So again essentially the distinctness of the EIs will tell you that if Z1 is one of these, then Z2 is the other one which is translated by 1 or tau, okay. So let me write that down. So let me write, say Z1 is half, okay, then Z2 has to be half plus tau. Z2 is to be half plus tau or half itself, okay. For otherwise, if otherwise phi of Z1 phi tau of Z1 is equal to phi tau of Z2 will contradict the that E1, so phi tau at half is E1 of tau, and you will get phi tau at any of the other 2 points which are tau by 2 or tau by 2 plus 1, it is E2 of tau or E3 of tau. I mean if otherwise if otherwise this will not contradict, this will give that this is equal to this or this is equal to this, which is a contradiction, okay. So we have settled all the cases when one of these points is one of these zeros, okay. So the only other case that is left is you have 2 points, both Z1 and Z2 are on the boundary, okay, and not any of these zeros and not any of those poles which are the vertices, and in that case you can make sure that both of them are on the same edge or an adjacent edge, okay, and in that case again you can join them by a path and find a simply connected neighborhood. You can translate this whole fundamental parallelogram a little, okay, and continue to apply this argument to get Z1 equal to Z2, okay. So so essentially what this will tell you is that either you will get Z1 equal to Z2 or you will get Z1 is equal to a translate of Z2 by plus or minus 1 or plus or minus tau, okay. So let me write that if both Z1 and Z2 are on the boundary and not among the zeros of phi prime tau of Z and poles of phi tau of Z and phi prime tau of Z, then the integration argument works to show Z1 is equal to Z2 plus or minus 1 or Z1 is equal to Z2 plus or minus tau, okay. The argument will give you this. So that finishes the proof of the fact that the proof of this claim, okay. So I want to just conclude by saying the statement that I wanted to originally say, that phi2 goes down to a map from the torus minus a point, it is a bijective map from the torus minus a point to this subset, okay. And you see what you must realize is that so for the moment this target subset is it is a closed subset, it is a closed subset of C2, okay, and a priori you can consider it only as a topological space. In fact it has a manifold structure, okay, in fact it has a Riemann surface structure, but that has to be explained properly, okay, which I will do in the forthcoming lecture. But if you just consider this as a closed subspace, topological subspace of C2, then what you get is that you get that phi sub 2 induces a homeomorphism of the torus minus this point onto this subset, okay. You get a homeomorphism onto this subset because you see basically at least for the moment it is a continuous bijective map. Maybe we'll need to do a little bit more arguing to say that it is actually a homeomorphism, okay. So let me record that and stop there. So let me write it here. So let this board be there as it is. So let me write it here so that I keep so we get so you can call this as a theorem phi sub 2 from the torus induces a map, a continuous bijection from t sub tau minus the special point which is the image of the lattice to this subset xi sub tau upper 2 considered as a closed subset of C2, okay. So essentially so this is the statement, and I will also call by abuse of language I will also call the induced map from the punctured torus to psi 2 as phi sub 2, okay. So we shall also call this induced map phi sub 2, okay. So I will continue in the forthcoming lecture. Essentially what I want to say is that you can so what I will be doing is that I will show that this C2 is an open set in the two-dimensional projective space, and this this curve, okay, this subset can be compactified by adding just one point, okay, and once you add that one point, then this continuous bijection from the punctured torus to that will extend to a homeomorphism of the full torus to the compactification with that one point, the so called point at infinity added, and then we will show that this is a homeomorphism, okay. So that is what we will do in the next lecture, right. So I will stop here.